This episode is brought to you by my friends at Patreon. If you'd like to join them and get early audios of upcoming episodes, please see the link in the description. And, once again, by Singularity G3, now in his 4th year as my illustrator. Well, what can I say about 2024? The Europa Clipper got off all right. James Webb reached the halfway point of its primary lifespan without a hitch. Oh, and Gaia ended its life after nearly doubling its predicted star count. All good things. Nice, optimistic exemplars of the forward march of human knowledge. Yes, it's fair to say that 2024 was a great year to be in space. So let's go there again. I present to you, my fellow seekers, the bottom 5 of the top 10 astronomical discoveries of 2024. Free-floating definitions. It is odd how astronomy so thrives on novelty, given that every one of its discoveries, bar the occasional supernova, predates human civilization. What astronomers consider new and exciting is simply the result of better technology unveiling what had already existed for millions, possibly billions of years. Our universe lies perpetually in shadow, and it takes a keen eye to pierce it. Cue the James Webb Space Telescope, which is leading the way to unveiling the next layer of objects in our galaxy, rogue planets, though astronomers still refuse to identify them as such. This isn't just willful obstinacy. There is genuine confusion as to where to draw the line between planet and star. In 2023, the JWST identified 42 rogue planets. Jupiter mass binary objects, or jumbos, within the trapezium, the raging cluster of giant stars at the core of the Orion Nebula. These were not the first free-floating planetary mass objects found. Far from it. But they were the first large sample of such objects to be found in binaries. Before then, it was assumed that the number of binaries would decrease with mass. More importantly, the existence of these objects in such wide binaries, each ranging from 0.6 to 14 Jupiter masses, and from 28 to 384 AU in distance, left no agreement as to how they formed. Did they form from direct collapse, like stars or brown dwarfs, or through core accretion, like planets? If they formed like stars, how did they get so small? And if they formed like planets, how did they remain tied to one another after being ejected from their system? This July, a team at Leiden University in the Netherlands ran a number of simulations to see which origin produced results in best accord with observation. They found that the most probable solution was that these objects formed in situ from collapsing gas, like stars. This is infuriating, at least to me, because at least some of those objects were less massive than our own Jupiter, which, the Juno probe had recently and annoyingly informed us, most likely formed by core accretion. If a stellar object can be smaller than Jupiter, can there even be an objective dividing line between planetary and stellar objects? And could we ever find one? As if to infuriate me even more, in April, Gavin Coleman of London's Queen Mary College, my alma mater as it happens, ran another series of 10 million year simulations showing that free-floating planets are efficiently ejected from systems during the epoch of formation, provided that those systems are binary, and that the planet initially orbited both stars at once. The simulations predict that for planets with a mass of between 1 and 100 Earth masses, the rates of ejection were as high as 7 per star. For planets above 100 Earth masses, however, the rate fell to about 3 per every 5 stars. One potential bright spot is that these ejections also generate very high initial velocities for their planets, far faster than those observed in star-forming regions, suggesting it may be a means to differentiate rogue planets from planetary mass stellar objects. But of course, things get more confusing. In August, a team out of Johns Hopkins University, employing the JWST, identified 6 potential rogue planets within the young nebula NGC 1333, located about 1,000 light-years away in the constellation Perseus. At between 5 and 10 Jupiter masses, they are among the smallest objects believed to have formed star-style via direct collapse. And not for the first time, one of those objects has been found with a protoplanetary, or perhaps protosatellitary, disk, meaning that it was in the process of forming a moon system like Jupiter's. But what truly confounded observers is what JWST didn't see in this particular run: any objects below 5 Jupiter masses. The team pondered if this may indicate that objects below 5 Jupiter masses do not form by direct collapse. But if that's the case, how do you explain the supposed examples of direct collapse objects of just 0.6 Jupiter masses? The word planet has been driving humanity mad since the ancient Greeks coined it 26 centuries ago. But until we can invent a better one, we're stuck with it. Is it time to probe Uranus? Okay, no more jokes. I don't even use that pronunciation. I use Uranus. It's truer to the Latin. Yes, I know Uranus is Greek, but it's Latin. Forget it. On the 17th of January 2024, Emma K. Dahl of the Jet Propulsion Laboratory, along with a multinational team, laid out the scientific case and specific goals of a combined orbiter and atmospheric probe similar to the Galileo mission to Jupiter, to our solar system's enigmatic, oddball, 7th planet. This was no mere whim. In 2023, the National Academies of Sciences, Engineering, and Medicine named a Uranus orbiter as the top priority in their latest decadal survey. From a scientific standpoint, the reasons for such a mission are self-evident. What knocked Uranus on its side? What creates its strangely lopsided magnetic field? Why is it so much colder than its more distant cousin Neptune? What maintains its degraded ring system? What created its crazy paved moon, Miranda? Do any of its moons possess internal oceans? Perhaps most importantly, surveys have shown that objects of Neptune and Uranus's mass, between 10 and 20 times the Earth, are the most common planetary objects in the universe. A mission to Uranus may finally tell us why. In the lead-up to such a mission, a team at the University of Texas is attempting to perfect a model that could reveal whether icy moons have internal oceans simply by observing their surfaces. All large moons in the solar system are tidally locked, and all tidally locked objects oscillate, or wobble, as they orbit. According to the Texas team, the bigger the wobble, the deeper the ocean. This would be a difficult result to get. A 150-kilometer deep ocean would produce a wobble of just 100 meters. In October, a paper co-authored by John Nordheim of Johns Hopkins suggested that at least one of Uranus's moons just might have an internal ocean. Its strangest moon, tiny Miranda. That's right. The moon that looks like it was mashed together with Play-Doh by a cosmic infant might actually possess active geology. But that very insanity of a surface could provide clues as to its interior. By examining the cracks, rifts, and ridges on its surface, and working back via a computer model, they were able to infer the existence of a 30-kilometer thick crust, overlaying a 100-kilometer deep ocean, sometime within the last 100 to 500 million years, likely during a time when Uranus's moons were in resonance with one another, creating tidal heating, like what is seen on Jupiter's moons, Io and Europa. The ocean is not likely fully cooled yet, since if it were, the ice's expansion would have left telltale cracks on Miranda's surface. In July, a second Uranian moon, Ariel, thanks to JWST, also hinted that it might be hiding an ocean. Using James Webb, a team of astronomers at Johns Hopkins found that Ariel's surface showed traces of carbon monoxide. This was insane. Ariel's surface temperature is 60 kelvins. Carbon monoxide's boiling point is just 8 degrees higher. There is simply no way for it to be there unless it is regularly replenished, presumably by cryovolcanism. On top of that, JWST also detected the presence of carbonate salts on Ariel's surface, which form in the presence of liquid water. If subsurface oceans could be detected in 2 of Uranus's moons, what does that imply for the other, larger and more regular ones? To say nothing of those around other ice giants across the galaxy. Speaking of those other ice giants, in October, Hubble and New Horizons, still searching for its next Kuiper Belt target, turned their joint eyes on Uranus, because, as Uranus represents the most common form of exoplanet, it could serve as a practice target to hone detection methods. By comparing data from Hubble, which is 2.7 billion kilometers from Uranus, with New Horizons, which is 10.5 billion kilometers from Uranus, it is possible to see how storms observed at relative proximity appear from a greater distance. They found that Uranus's brightness did not change appreciably with the rotation of the planet, suggesting that, despite its momentary fireworks display some years ago, it has returned to its iconic blandness. In November, a team at Imperial College London published a paper concerning the anomalous cooling of Uranus's atmosphere, or at least the topmost part of it. Telescopic observations since Voyager 2's flyby in 1986 have seen the temperature of Uranus's ionosphere, or thermosphere, drop by half in 36 years, an effect apparently unique to that planet, and unlinked to Uranus's seasonal cycle or to the Sun's 11-year sunspot cycle. However, it does appear to correlate with a slow drop in the intensity of the solar wind, observed since 1990. This has allowed Uranus's magnetosphere to expand, further shielding it from the solar wind and lowering its upper atmospheric temperature. I'm not sure how I feel about a mission to Uranus. Yes, from a timeline standpoint, it makes sense. NASA's mission philosophy of flyby, orbiter, lander, rover, soon to be maintained with Europa and Titan, demands that Uranus is next in line. But beyond its name, our hapless 7th planet has never gained the public's affection the way Saturn, Jupiter, or even Pluto have. This is partly due to its inauspicious flyby, which happened to coincide with both the Challenger disaster and the return of Halley's Comet, and also because it missed its beauty shot by a good few decades. If Voyager 2 had arrived at Uranus 20 years later, we would have observed a far more vibrant world than the flat aquamarine void that fills most textbooks. Finally, the trip would be monumental. If we scale Cassini's travel time to Saturn to the distance of Uranus, then the travel time to Uranus would be 13 years, as long as Cassini remained in orbit. During that time, it managed to observe Saturn for almost half the planet's year. For a Uranus probe to do the same, it would need to remain in orbit and functional for 40 years, something no satellite, even of Earth, has ever done. A long hiatus in Uranus's gloomy environs. Would you like ketchup with your aliens? I don't know about you, but I'm getting sick of the Great Silence. Whatever reasons aliens have for not contacting us or letting us know of their existence, it's worn out its rationale for me. Honestly, at this point, I'd probably be okay if they just invaded us. And it seems I'm not alone, because in May, a group of scientists from across the world published the results of what they roaringly call Project Hephaistos, after the Greek god of the forge. If patience and delicacy won't work, the title seems to cry, we will hammer out alien contact by sheer brute force. So how are they going to do it? Dyson structures, of course. For those not in the know, in 1960, astrophysicist and dreamer Freeman Dyson envisioned a future civilization so powerful that it could construct a swarm of continent-sized habitats dense enough to block out their star, harnessing all that power for themselves. While Dyson spheres have often been portrayed as gigantic hollow shells, such a structure would be physically impossible without Star Trek technology. Even a full swarm, like Dyson initially envisioned, would require more heavy elements than exist in any one solar system, including in the Sun. So, the team pondered, how about half Dyson swarms? Dyson oysters, if you will. How would they impact the light from their stars? To find out, the team performed a massive data mine of the three most recent comprehensive sky surveys, Gaia, WISE, and 2MASS, combining optical and infrared observations of 5 million individual stars to observe the excess infrared that such a structure would produce. Of course, many other things, such as dust disks, produce an infrared excess as well, so the team then applied a filter process, which, once completed, left them with a total of 7 candidates, all red dwarf stars, described as, quote, clear mid-infrared emitters with no clear contaminators or signatures that indicate an obvious mid-infrared origin. Debris disks can be ruled out, they argue, because they are extremely rare around red dwarfs. But this is the search for extraterrestrial intelligence, where no discovery can go undoused with questionable water. The same month the project published their findings, another team cross-matched their results with those from several other surveys, and looked for radio sources within 10 arcseconds, or a 360th of a degree, of the mooted megastructures. They found matches for 3 of them, all extragalactic. They were, in fact, hot dogs, or hot dust-obscured galaxies. In September, a paper noted that about 1 in 3,000 quasars is likely to be obscured by dust, and thus produce the effect seen, meaning that megastructures are more likely to be hot dogs than not. At least, so they argue. But the search is never-ending. In December, another team argued that, rather than a sphere, a Dyson ring catching a pulsar's beam would be a far more efficient use of resources, and recommended we use pulsar timing as a more certain means to detect Dyson structures. Even excluding that, 4 of the initial team's final 7 candidates remain undebunked, regardless of how ready others are to brush them off. The mystery still draws us on, and at least if we didn't get aliens, we got hot dogs. Spin the discs and get this party started. If there's a running theme in the age of James Webb, it's that everything seems to have got going a lot sooner than expected. Later in this list, we will see how that applies to stars and galaxies, but as several surveys have found this year, even planets seem to have barged past the bouncer in the hurry to join the club. Fittingly, in January, Cheng Han-xia, a PhD candidate at Yale, presented a series of follow-up observations to a now iconic series of images of protoplanetary disks taken by the Atacama Large Millimeter Array, or ALMA, in 2018. These observations were of older Class II disks. Xia's follow-up survey was of younger Class I and Class 0 disks, whose parent protostars are still collapsing and forming. A Class I protostar only remains such for a few 100,000 years, and a Class 0 for just 10,000 years, and yet the survey reveals surrounding disks already replete with assumedly planetary gaps. Common assumptions about solar system formation suggest that even the fastest forming planets take at least a few million years to form. It is not yet known whether these gaps are due to the presence of Earth to Neptune-sized planets, or simply transitory artifacts of the formation process that will soon be washed away. If they are planets, then our assumptions about planetary formation are thrown face first on the pavement. A possible resolution to this conundrum appeared in August, when a German-led team developed a new model that allowed for planetary formation at hyperspeed. According to the model, ring-like troughs form in a protoplanetary disk that trap material and prevent it from migrating inward. Not only does this allow for the formation of cores in as little as 300,000 years, but the resulting pressure also induces a chain reaction of formation, allowing for gas giants to form in quick succession. As each gas giant forms, it prevents the material from the subsequent region from migrating, allowing further giants to form. In December, a Europe-wide team employing JWST performed a follow-up of sorts to a finding made by Hubble in 2003. That year, the venerable space telescope detected a planet in orbit around both a white dwarf and a pulsar, the first circumbinary planet ever found. What confounded observers of this new planet was its age, which, at 12.7 billion years, is close to that of the universe itself. This made no sense. How could a planet estimated to comprise about 2.5 times the mass of Jupiter have formed so early in the universe's history, when the universe was still mostly gas? Few stars had died, and thus the metal, astronomy speak for elements heavier than hydrogen and helium, needed to form planets had yet to be released from their cores. While distance won't allow the team to observe star formation at the dawn of time, the universe has provided a decent substitute, the Small Magellanic Cloud, one of the closest galaxies to Earth, which happens to also be extremely metal-poor, thus simulating somewhat the conditions in the early universe. And within the Small Magellanic Cloud, the team located dozens of young stars, between 20 and 30 million years old, surrounded by protoplanetary disks. Except protoplanetary disks aren't supposed to last longer than 3 or 4 million years. It would appear that in situations of low metallicity, protoplanetary disks can persist for 10 times longer than they do in metal-rich environs. Well, that would explain the presence of large planets in the early universe. The only question is, why? One speculation is that, in times of low metallicity, sun-like stars form from larger clouds of gas, and so with their higher gravities, gather larger protoplanetary disks. Just as current discoveries are challenging assumptions about how planet formation begins, others are complicating our understanding about how it ends. In March, Naman S. Bayai and colleagues published the results of a JWST survey of T. Chameleontis, a protostar about 100 parsecs from Earth. The gas in TCA's dust disk is already dissipating, suggesting it has reached the end of its era of planet formation. Its disk contains a gap 30 AU wide, or about as wide as our solar system. Given that TCA is within the mass range of our Sun, it seems likely that when its solar system finally forms, it will broadly resemble our own, meaning that that gap likely represents the planets already formed. The end of planetary formation in stars is believed to be triggered by the disk wind, a blast of high-energy radiation from the young star that disperses whatever gas may remain within the disk nebula. The team employed JWST to track the path of TCA's disk wind, using neon as a marker. This is the first time a disk wind has ever been imaged. The team estimates the system is losing a moon's worth of mass every year, which is in keeping with models and predictions. TCA has also seen a 50% energy increase since it was last imaged by the Spitzer Space Telescope in 2006, indicating that it is preparing for ignition. In May, 2 papers were released concerning IRAS 2377, an infrared source first logged by the satellite IRAS in 1983. In 2016, the Pan-STARRS survey identified it as a protoplanetary disk viewed side-on. The 2 papers, employing follow-up data from the Smithsonian Astronomical Observatory's submillimeter array, finally reveal 23077's nature. Not only it is a protoplanetary disk viewed side-on, like the well-known disk Gomez's hamburger, but the largest protoplanetary disk ever seen, with a radius extending out to 1500 AU. The young star at its center is believed to comprise between 2 and 4 solar masses. In honor of Gomez's hamburger, and the Uruguayan and Romanian heritages of the team members, the disk was christened Dracula's Chivito. In July, a multi-institutional team, using TESS, NASA's Kepler successor, for the first time captured a key moment in planetary formation, the creation of a hot Jupiter. Ever since they first showed up and scrambled the brains of astronomers everywhere, hot Jupiters have thumbed their noses at theorists. The vast majority of material in the universe is composed of materials with low melting points, like gases and ices. Giant planets required more material to form, and so could only do so at great distances from their stars, where such material could persist. So how could an entire class of Jupiter-sized objects end up at distances from their stars so intimate as to make Mercury seem COVID-appropriate. The only answer was that they must have migrated inward to their current orbits. Question was, how? Well, it now seems we have the beginnings of an answer. By tracking the orbit of a gas giant in a binary system with a number for a name, the team found that it swung from 1/10 the orbit of Mercury, hot Jupiter distance, to roughly Earth's distance from the Sun. Even more bizarrely, its orbit was retrograde, meaning that it orbited its twin stars in the opposite direction to their rotations. This could only have happened if the gravity of the two stars had knocked its orbit sideways, placing it on its current wild trajectory. Every time the planet brushes by its star, the star pulls at its orbit, and eventually, the team calculate, and by eventually I mean in 1 billion years, its orbit will lie entirely within that star-kissing distance. Given that not all hot Jupiters are found in binary systems, this solution can only work for some of them. But it is another step on the path to grasping just where these cosmic clowns got their giggle from. Daddy's angry. I have often described the sun as the closest thing to a god in our corporeal, observable universe. But if he is a god, he's one of the old ones, violent, capricious, and uncaring whether we live or die. And make no mistake, if he wanted to, he could kill us. We are just one sliver of ozone away from learning just how powerful and destructive our unpredictable dad can be. Having long ago given up sacrifice as a means to deal with such behavior, we now watch him day and night with an armada of spacecraft, recording his every twist and tantrum. We have known for nearly 2 centuries that the sun undergoes an 11-year sunspot cycle, during which observed solar activity waxes and wanes. And right now we are in the middle of a solar maximum. In fact, we are in a bit of a maxed-out maximum. Contrary to experts, who predicted a mild or diminished solar maximum much like 2012, this year is currently seeing activity half again above normal. We've already seen a few low-end satellites fall to Earth ahead of schedule, not to mention aurorae in Germany and California, closer to the equator than they've been in 20 years. For all the great Instagram shots, space nerds would be right to bite their nails. A sufficiently powerful solar storm could knock out electricity and telecommunications worldwide. No power, no food, no water, no communication. For weeks. Scientists estimate that the cost of a truly devastating solar flare could run into the trillions, and from the looks of things, they happen about once every solar maximum. Given that any flare has about a 5% chance of hitting Earth, we should expect to see such an event about once every 440 years or so. The last one was in 1859, so when 2300 rolls around, remember to mark it with a paper calendar. But there is evidence the sun can do far worse than that. Radioactive traces in ancient trees and glacial ice suggest that Earth was subjected to flares 10,000 times stronger than those known today. In December, a team at the Max Planck Institute conducted a survey of hundreds of sun-like stars to catch one of those so-called superflares. The team scoured Kepler's database for 56,450 stars and a total of 220,000 years of observed solar activity. The team was exceptionally conservative in their selection, only choosing the most sun-like candidates and the most obvious activity, but nonetheless managed to identify superflares on 2,587 stars, which means that the sun might produce a superflare about once per century, which in turn means that one would strike Earth about once every 2,000 years, roughly in line with the geological record, which suggests one every 1,500 years. It would be nice to know when the last one was. Apologies for the delay, fellow seekers, but I really wanted to do an end-of-the-year list, even though it seems to get harder every year. The second part will be far more difficult, so I'm not sure how long it will take. I think in future I might simply stick to short videos released as news develops. Thank you for waiting, and I will see you again soon.